Okay, please focus. Please focus. So the question is, if these are the values of x, x is equal to -2, x is equal to 0, x is equal to 5, x is equal to 9, and these are the corresponding probabilities, what is the expected value? Okay. So the solution is very simple in this particular case, and if we see, this is simply the multiplication of the probability with the corresponding value, then the probability with the corresponding value, and so on, and then adding all those. Thanks. Focus now. So 0.1 into -2 plus 0.4 into 0 So whatever that value is, that's the result. Okay, whatever that value, you may have calculators. 3.5? 3.5. Now, the next question is just having squares of these numbers. So the expected value of y is 0.1 यार आप खड़े हो जाएं, आप खड़े हो जाएं, आप पीछे वाले को कह रहे हैं खड़े हो जाएं ज़रा। आपको पहले कुछ नहीं आता, अभी आपने बताया कि आप बड़े लेट थे और अब आप फिर बातों में लगे में। आपसे कह रहा है वो, क्यों जी, ये कौन इससे कह रहा है, ज़रा वो खड़ा हो, खड़ा करें जो आपसे कह रहा है ये। हाँ जी बताएं, आप खड़े हो यार। हाँ जी, वो तो उसने तो नहीं कहा। हाँ जी, इसने बुलाया और आपने तवज्जो दी, तो मैं जो यहाँ पे खड़ा हूँ मैं भी तो आपसे ही मुखातिब हूँ, हैं? सॉरी क्या होता है जी? मेहरबानी, बैठे यहाँ। 0.3 into 81, and what's the result? So that was the solution. And if we remember from the very last time, we generated data according to a particular distribution, and then we just pick an average. Just add all the numbers, divide by the total numbers, and we get exactly the same number, which is the expected value. Why that happened? Okay, let's see why that happened. For example, if you generate data, if you write a function and generate data according to this distribution, 10% of the total data will be -2. If you generate, for example, 1,000 numbers or 1,000,000 numbers, 10% out of those will be -2. 40% will be 0. Okay. 20% will be 5, repeated 20% of the total, and 9 will be repeated 30% of the time. Yes? That we tested last time. Now, if we just take the average of that data, let's say that data has 1,000,000 entries. Let's say n is equal to million. How many are there? Million? Is this million? No. Is this million? Okay, let's say this is million. And we take the average of all the numbers. So all the numbers would be, let me call them x1 plus x2 plus x3 xn, which are total millions. Obviously, x1 will be one of these numbers, x2 will be one of these numbers, and so on. Yes? Okay. And then we divide this by n, and it turns out, in this case, that result also will become 3.5. Yes? Why that happens? Let's see. If we just rearrange all these numbers and just place all the minus 2's, so these are all the minus 2's. I mean, out of these are minus 2's, minus 2 plus so on. These are total 10% of the total data. We just sort them, arrange them, and these are all, let's say, zeros. This is the same sum but rearranged. We just put all the minus 2's together, all the zeros together, then all the 5's together, and let me write here all the 9's together, okay? And then we have this n. Yes? This is the same thing as above. Make sense? Okay. How many 9's are there? Well, they are 30%. 30%. And what is the 30% of n? Yeah. What is 30% of a million? Ji? What is 30% of a million? 3,30,000, I guess. 3,30,333. Yes? Okay. See, please. I can write that number, which is, yes? Okay. So we have all the 9's. Is this okay, or should I zoom it more? Is it visible? Maybe I can change the color as well. Is this fine? Then we have minus 2's. Then we have all the zeros. And then we have all the 5's divided by n. Yes? Now the total number of 9's will be, because we have generated data according to this distribution, the total number of 9's will be 30% of the total data, which means the 9's together will be 3,03,000, 30,000. I guess this number multiplied by 9. Yes? That's the same thing? Yes? Plus, how many minus 2's are there? Sorry? 33,333. Oh, 30%. Yeah, sorry. That will be 3 lakh, I guess this thing. Yes? 3 lakh, yeah. Into 9, yes? Plus, how many minus 2's are there? Minus 2's are 10%. So they will be, in the data, they will be these many. Plus, how many zeros are there? 40%. Plus, how many 5's are there? 5's are 20%. divided by a million, which is n. Yes? Make sense? Now, this is, by the way, this is simple average. I was just taking the average and I'm just rearranging the numbers. This is simple average of a lot of numbers. Yes? Okay. Now, you can see we have this thing. I can just write the n separately to each fraction. Yes? Then we have make sense? That's the same average. Yes? What is this number? 0.3 into 9 plus. What is this number? 0.1 into minus 2. What is this number? 0.4 into 0. What is this number? So what's the lesson? If you generate a lot of data according to a certain distribution, then the average of that data becomes expected value. And if you do not want to generate a lot of data and still want to find out the average of the data, if I could have generated a lot of it, and you are available with the distribution, just go and find out the expected value. So the expected value is the average of data. If you have generated the data, a lot of data, according to the distribution, then the average of that data is exactly the expected value. Make sense? Yes. Now here is a catch. What's the difference between expected value and the average? Well, the expected value is the average if you generate the data large enough. By large enough, I mean a million, a trillion, maybe 100 trillion. If you generate a lot of numbers, then the average will become expected value. Because whatever numbers you have generated, that is called a sample. See it? Last time we have generated, I guess, 100,000 samples in the code, remember? I guess we have if you see, we have generated, I guess, a million. Last time we generated a million samples. So that set of numbers is called a sample. Okay? Sample from a distribution. Now, if we take the average of the sample, that average will become expected value only if the sample is large enough. So think about generating just 10 numbers out of the distribution and then taking its average. That will be far away from the expected value. Because in 10 numbers, the actual respect of the distribution would not have been captured. Is that understood or no? Let's see again. Let's say we generate only 100 numbers from a particular distribution we did last time. And you can see the fractions that appear in the data, they are different than it should have been appeared according to the probability distribution. And this is because we have not generated a large enough sample to respect this distribution. It will become even worse if we generate very small sample. You see that? Yes. This is the actual proportion the sample should have. But the portion the sample should have will only be there if you generate very large sample. So for large samples, their average is what the average should have been according to the distribution. Make sense? So here is the difference. The sample average, or sometimes called the sample mean, what is the expected value and what is the sample average? Well, do you know already the idea of population and sample? Do you know the population? What is population? Yes, no? Let's say, listen, let's say you want to study a particular reaction of a medicine in the people of Lahore, let's say. You want to introduce a particular medicine, you want to inject a particular medicine, and you want to study what that medicine, what reaction that medicine, or what kind of remedy that medicine can cause in the people of Lahore, because this area has this particular humidity level, this area has this particularly dust level, and people normally have this kind of food intake, and so on. So these are the factors, and now you want to just test this medicine on the people of Lahore, let's say. So you have medicine, you go and you check the reactions. One possibility is you go one by one, starting from the youngest person to the oldest person of Lahore, and just inject the medicine to all of them, and then get the results and make some conclusion on that. This is called testing on population. That's the whole set possible. Make sense? But normally what you could have done, or what has happened, is you will go in different places. For example, in one particular place, and you will ask 2 or 3 volunteers or somebody, come and you inject the medicine, and then you go, I mean, there may be 1 million people there, but you just pick, let's say, 100 of them randomly, and you inject medicine. Then you go somewhere else in Lahore, in another area, you select a few people, maybe randomly, and just inject the medicine. And let's say you total have 1 lakh people out of so many people of Lahore. Now this 1 lakh people that you have selected, this is called the sample. You have collected a sample. Make sense? And you then study the characteristics of the sample, and you say, from the sample, you say, okay, the population or the Lahore people have this much reaction from this medicine. And this is what all the times that happens in statistics. By the way, when you want to test your blood cell count, I guess, what is that called, the test? CBC. Count blood cells, I guess. Complete blood count. They do not extract all of your blood. If they do, that's the population they have, blood population. Make sense? What they do is you pick the sample, study the sample, and then they say the blood has this much characteristics. Make sense? Most of the time, the underlying distribution, this is the distribution. Underlying distribution of a particular data, a particular phenomena may not be available. Then we go, we pick the sample, we measure certain characteristics from the sample, and we make large enough sample, and then we study the sample and think about that the population or the underlying whole factory or something has this much characteristic. Make sense? And what I'm showing you is that if you just want to compute on average what is happening to the population, that average can be computed by a sample as long as you pick the sample large enough. Pick the sample, take its average, and that is what the average of the population, the expected value that you compute by the distribution, is the average value of population. The average that you compute from the sample is the sample average. The sample average will become population average, or it will become closer to the population average as long as you have sample size large enough. Make sense? Because if we want to study something, people will not give us probability distribution. This is the random variable, these are its values, these are the probabilities, now go. We have to pick sample, we have to build distributions, we have to build averages and all that stuff, and we will not be knowing the probability distribution in reality. So all we have to do is to work with the samples. Make sense? Okay, great. Just one last thing about this thing. That the sample average, it becomes close to the population average, which is the expected value, if the sample size is large enough. This is a particular law, and this law is called law of large numbers. What is law of large numbers? Law of large numbers. One over n this x belongs to the set of sample. So consider S as an array or set in which you have collected the sample, and n is the total size of the sample. This will become the expected value of the random variable if the sample you have picked is large enough. And this is how we denote something is huge. This is the sample average. This is the sample average. This is the population average. The sample average will correspond to, actually this is not equal sign. This is tends to. This is this sign basically. Tends to. It will become closer and closer to the actual population average if your sample size becomes large enough. If your sample is small, based on the small sample, whatever conclusion you have come up with, it may not be applicable to the population. You should have gathered a larger sample. And it is common sense, by the way. Yes? So this was particularly the reason why the average of the sample, if the sample is large enough, it becomes the expected value. Okay? So what is the formula for expected value? You have already gone through it, but let me just write formally. The expected value of a random variable x is simply the sum of all the values. Should I call set S or? I mean, the set S contains that's the sample space of random variable. These are all the values the random variable can have, 0, 1, 2, 3, whatever. X, P of x. Okay? That's the formula. Now, one more thing that I want to focus on. What is this? I've just given you squares of these with the same probabilities, and I asked you to calculate the expected value. I could have, rather than writing y, I could have written x square, the random variable x square. Yes? But I intentionally wrote y. Later on, I will replace y with x square. Okay, there is an experiment, for example, in which you do the experiment and the random variable x has a value -2 with probability 0.1. So your prediction is that the random variable x will take value -2, and the probability of this happening is 10%. What is the probability that the square of that value will be 4? The same. The same. Yes? If the underlying experiment is same, for example, what's the probability that the next the next experiment outcome in terms of random variable will be 0? Okay, 40%. What's the probability that the next number plus 1 is 1? 40%. Because the next number plus 1 is equal to 1 means the actual number is 0. What's the probability that the square of the number will be 81? Well, that's the probability that the number will be 9. Make sense? Yes, no? Clear? Okay. So that means what is the expected value of y? Well, that is again y into p of y. But it turns out for a particular value of y, p of y is exactly p of x. So for example, if y is 4, this is p of x is equal to 1 minus 2. Yes? If y is equal to, for example, 0, this is the probability that y will be 0 is the same as x is equal to 0. The probability that y will be 25 is the same as x will be 5. So the expected value of y is just these numbers with the probabilities of x. Make sense? Yes, no? So the probability, yeah, go on. मैं दोबारा बता देता हूँ. इनको कह दें यार, इनसे 1:30 बजे हैं. कह दे, कुछ नहीं होता. अब इस पे बहस शुरू होगी कि 1:30 बजे क्यों आना है. चलो, सी अगेन. Let me expand it. Probability of expected value of y. This is y, which is this is 4 into probability that y is equal to 4. Yes? And that is x is equal to minus 2 plus. That's how we compute expected value of any random variable. Then 0, then the probability that y is equal to 0. 0 into probability that y is equal to 0. Probability of y is equal to 0 is x is equal to 0. Probability that x is equal to 0. Because y is simply square of x. Plus the next value of y is 25 into probability that y is equal to 25. That is x is equal to, the probability that x is equal to 5 is the same as probability that y is equal to 25. Because when x will take value 5, then y will take value 25. Because y is not a new experiment. Y is just another random variable on the same experiment. And it is derived from x. So it depends on x. Yes? Yes. Then what is the... Yes? So if I replace y into x square, what is the expected value of x square? That is simply this is the formula. Make sense? Yes, no? Is this okay? Okay? Everyone? This is not simple, by the way. This is sometimes tricky. If you understand it, it's good. Good. In general, Give me a minute. Okay, expected value of some function of a random variable, that function can be any function, is summation over all the x in the sample space, that function value into probability of x. This should be known. Clear? Yes, no? Yes. Okay. Let's test your understanding. Let's see. No solution, no solution. This is fundamental problem. So just let them do. So this is the distribution of x, and your goal is to find out the expected value of x square plus 4. X square plus 4. Come on. This is the formula you have. Hurry up. So all of you, I guess, are working on these lines. It's 16 plus 4, 20. 20 with the probability of 4, which is 0.2, plus 1 plus 4, 5, into probability of minus 1, which is 0.1, plus 81 plus 485 into 0.4, plus 5 again, the probability is 0.3, and whatever that result is. Yes? Whatever that result is. Is this okay? Okay, a few more things. I already have taken your classes like 20 minutes, 30 minutes. It's 1 hour 30-minute class. And still, even if we go to this number 1.5, it still become not more than an hour. So let's continue. Let me ask you something. Given this distribution where you know that x equals to 4 can appear with this probability x equals minus 3. I mean, if I do experiment, more likely x is 9, but I'm not sure. But the best guess I can do is 9 because it has the maximum probability. But still, the value of x is random. Yes? Given the distribution, if I want to do the experiment one more time, which value of x will appear that is random? That's why this is a random variable. Is this number random? This is a number. Like the value of x is equal to 4, the value of x is equal to minus 1. These are numbers. X is a number. Expected value of x is also a number. X is random. We cannot predict it. What about expected value of x? Without doing the next experiment, if the probability distribution is given, can we have for sure this is the expected value of x? No? Yes? So the question really is expected value random or not? If you cannot tell for sure that the expected value will be what in the next trial, then it is random, otherwise it is not. A related question, by the way, is expected value dependent upon the experiment? I mean, given the distribution, if you do an X trial, will the expected value change? No. Given the distribution, this is the way to compute the expected value. If you do the experiment, the value of x can change, the next output may be different. But the expected value is fixed given the distribution. Expected x is a random variable. Expected value is not. It's constant. It's not random. Make sense? Yes? Yes? So this is the distribution. If I do the experiment, what will be the next value of x? Well, I do not know. This is the distribution. Whether you do the next experiment or not, this is the average value. Average. Average means if you do that experiment 1 trillion times, this is the number you will get on average. That is fixed. That is fixed. Make sense? So the expected value of a random variable is not random. It's constant. It's fixed. Okay? Great. Yes? Yes? I just multiply this separately, and split the summation. Is that okay? Yes? Why this is 1? The sum of all probabilities is 1. That means expected value of x plus 4 is expected value of x plus 4. Make sense? That's a simple, and this is not just 4, I mean you can call it expected value of x plus a, where a is not random, it's fixed. That is expected value of x plus a. Make sense? Yes? One more thing. Yes? Agreed? Agreed on it? Agreed? This becomes a times yes? Any problems here? Yes, no? Is that okay?
Yes, sir.
Okay. Can anybody tell me what's the answer? Hint. This is simply a constant. That's a hint. That's the formula. Expected value of x plus a. This is a. Yes? That becomes 2. Make sense?
Yes.
Okay, good. You can simply prove this, not a big deal. Yes. Okay? Yes, no? I've just computed the expected value of this. So a is out because of this, a is out. So you can just, by the way, do you know about derivatives?
Yes.
If you compute derivative of this quantity, what happens? Let me relate expected value with derivative, although there is no relationship at all, but let me relate it. How will you compute the derivative of this quantity? A common derivative of x square plus b common derivative of x plus derivative of the constant, which is 0, but let me write. Yes? Just treat expected value like a derivative. It goes inside exactly like the derivative goes. Okay? And if I have to tell you more generally, every linear operator does this. You need not to understand it completely what I'm saying right now, but just for your record, an operator is called linear if it distributes like this. It has more definition as well. Expected value is a linear operator, derivative is a linear operator, integration is a linear operator, and there are so many others. They just move like the derivative moves. Okay? But I'm sure you're not understanding what is linear operator. That is fine. If after 3 or 4 semesters you come up with linearity or linear algebra or somewhere like that, then you will understand what is linearity and you may then refer back to this concept. Okay? One last thing and then we will be quitting. What is this? Well, it is good to first open up this thing. This will become x square minus 2x yes? Now apply expected value in it just like derivatives. Let me apply in a whole first and then we iterate. This becomes this and that, they are constant, they are common. So now I'm taking expected value of this. Yes? This is constant, expected value of this number is the same thing. Make sense? So expected value of x square minus 2 times expected value of x whole square plus expected value of x whole square. So minus 2 plus 1, this becomes, I'm writing here, expected value of x square minus expected value of x whole square. Yes? Because this is 2 times y plus minus 2y plus y, this is simply 1y. Yes? Last step. Let me, this is this thing by the way. So 2 minus 2y plus y is simply minus y. Yes, no? That's the formula, okay? And this particular, at the end of the day, expected value of anything is a number. This is a number. And this particular number is called variance of x. We will study variance more. I guess you have heard these names, mean, variance. This mean is expected value. Variance is expected value of this particular thing, which is x minus expected of x and so on. This is called variance. And we will study variance more from the next class onwards. Okay? Thank you.